Welcome to another video explaining the universe using the particle model. Well, today's video is about preliminary results of experiment number 2, where I attempt to find the value of two constants in my equation for particle model equations for circuits. And one of the values is the interaction factor, and the other value is the number of volts per G1 particle. And unfortunately, results don't look very good. Now, the three previous videos I gave one here was on the experimental results of a 3-resistor experiment, and that turned out quite well. At least I thought so. I got a 70% and 80% correlation between the prediction of the particle model and the measurements made in that experiment. Then I explained this one. I'm giving the results today of an experiment that I explained what I was going to do and what I was hoping to find. And then I also explained experiment number 3, all about parallel resistors. That was a very interesting one. I hope you saw that one. Okay, so I then developed equations for I sub f and v sub g, and now you would think that I could solve for 7 unknowns using 7 independent equations. Maybe they weren't independent like I thought they were, but that's what I had, and that's what I tried to do. And I was able to get these equations down to two equations, but I had 4 unknowns, and that will not get me a solution. I'm going to try later and after some period of time in order to let this thing settle in. But for now, I did find a simple equation to get a value for I sub f. But nothing. I never developed any equation for v sub g that would allow me to calculate these values. Okay, well, it was clear from the beginning that the values were not coming out like I hoped. First, the values of current through each resistor was not as predicted. Second, the equation to find I sub f that I thought I had, I did get one, but it turns out it was either wrong or I did something wrong because I got negative values. That doesn't make sense. But I did develop a simple equation for IF, but then, as I said, nothing for V sub G. So what I did was I used 2 resistors, and so I'll start with the 2-resistor circuit, which is part of this experiment. This experiment was called the 2R 3R experiment, where I measured voltages and resistances of a circuit with 2 resistors and then with 3 resistors. And so if you look at the voltage drop across R1 in terms of the particle model, the voltage drop is equal to the number of G1 particles, B in this case, entering the large resistor. And you multiply that times this interaction factor, that's one of the constants I'm looking for, times the value of the resistance. This number in bracket, I don't know any of these numbers, but these numbers in this number in bracket is the number of G1 particles lost. This identifies the percent of these lost by virtue of that factor times the resistance itself. Number lost is this many. Then you multiply that by the volts per particle. This is the number of particles. This is the volts per particle. It gives you volts. So I have a voltage equation. But I what I did was I solved for current using the same equation. If you want current, you divide V sub R1 by R1, and the R1 disappears here and appears over on the left side, so you got V R1 over R1 equal to B IF VG1. Current through this resistor. Current through resistor 3 is similar, but the number entering the R3 is D. That's different than B, but it's the same type of current. Voltage across R3 divided by R3 is the current, and it equals D times IF times VG1. But D, it can be calculated. Like you can calculate the value of D by knowing what's going on here. And D is going to equal the number entering here minus the ones lost. Well, this is the ones lost, B. That's lost. So you have that, and that simplifies to B times 1 minus IFR1 times VG. So this this equation becomes this one, and now I've eliminated the value D. This is no longer part of that equation. It's simplified. Okay, so I have those two equations, and I'm now going to take the ratio of the current through R3 to the current through R1. This is the current. This is the voltage over resistance is the current, is the equation I just showed you. This is for R1. I showed you that. And when I divide this current into here, I get IR3 over IR1. And then on the other side, I get this term divided by this term. Well, if you look at that, B cancels out, IF cancels out, and VG1 cancels out. This was one of the problems with getting the solution, is the terms just kept disappearing on me. And the three unknowns are all gone except this one, which is interesting because when this one is still there, I know what IR3 is because I measured and calculated. I know IR1, again, I measured and calculated. I know R1. So I can find IF by reorganizing this into this form. This is what I did to find I sub F for the 2-resistor circuit and the 3-resistor circuit. Okay, so here's the 2-resistor circuit, and you measure the voltage drop and the resistance. Those are measured values. Current is not measured, it's calculated. It's calculated volts over R. I mean, that's Ohm's law. Even if you use a current meter, what a current meter does is you insert in series right here a shunt resistor, and the current meter reads the voltage across the shunt resistor, and it knows what the shunt resistor is. So it takes the voltage measurement, divides it by the shunt resistor, and displays the current. The meter does the calculation. So current is not real. So I've mentioned this in another video. Current's not real. It's a calculated value. And what I'm expecting in this result is the IR3 current is less than the IR1 because D is less than B. And the ratio of voltage to resistance should give me the current, but there is this one small difference. And this is the result. Well, this is the current through IR1, which is supposed to be greater than IR3, and this is the difference, and it should all be positive. Well, in this case, they are all positive, but what I did was I forced the spreadsheet to only display 6 decimal digits. So the significant digits I'm looking at are here, the lower 3 digits. And when the spreadsheet when I subtract this from that, I get 0 all the way through. That matches Ohm's law. I mean, if you did this experiment in college or even in high school, and you said, your teacher would say, hey, look, Ohm's law works, because you're only looking at a certain significant digit. But I used a 6.5 digit voltmeter to do the measurements of voltage and resistance, calculated the current, got this, and that's to be expected. I displayed that just to show that if you do this experiment yourself with an ordinary meter, you're not going to get results like this on this side. So all I did here was change the number of decimal digits displayed to 10. So I've added 4 more digits down here at the end, and when you do the difference there, it shows up, and it shows up badly, poorly. There are only 6 circuits: Circuit 1, Circuit 5, Circuit 8, Circuit 9, Circuit 14, and 15. I did 15 different circuits, all different values, only 6 of them. You rightly could conclude particle model failed. Well, let's move on and see what we could do. Well, the 9 values are negative and will not give me a valid answer for IF or V sub G1, but really just IF. Only the 6 that show a positive difference could actually give me something. Given that the difference are at the low level of a 6-digit meter, the results of any, if any, are suspect. But I did it anyway, because you learn something by going through the analysis. And here's the calculation. This is for the 2R circuit, and there's the 6, circuit 1, 5, 8, 9, 14, and 15. These are the actual measured voltage by using the 6.5 digit meter. You can see how I'm getting, in some cases, a lot of digits and not so many in other cases. Depends on how it comes out. The spreadsheet did the calculation. This is a 10-digit display. This is the difference. These are all positive differences. And this is that equation for I sub f. And look at the range. The red is the highest value, 4 times 10 to the minus 8. Lowest value, 7 times 10 to the minus 11. Well, I mean, that has a ratio of almost 1,000 to 1. Isn't pinning it down very well at all. And probably due to the fact that these measurements are so based on these lower digits. Well, impedance may have some to do with it, and I tried to look into that a bit, and we'll see how that turns out. But the results aren't very good, but maybe if I have a better meter, a better power supply, maybe a better procedure in doing this, maybe I can tighten that up and get more samples that are positive and the value to be better in a better range, a closer range. Well, I did the 3R circuit using the same equation. Now, interestingly enough here, the equation I developed for the 2R involved R3 and R1. So I just repeated it. So that's for this resistor and this resistor. But you can also get a calculation for R1 and R2 and R2 and R3. You get 3 different sets of equations and you get these results. Okay, not one give me a positive across the board. If I'm really going to get an answer for I sub f using these, I need them to be correct across the board. Not this one's wrong, these two appear to be correct, but the fact that this one's wrong makes me suspicious of these. Very poor results. Might even consider it a failure. Well, I tried to find VG1. I never got the equation for VG1, but while working on it in the spreadsheet, I found the number of G1s entering always the VG1 and B also seem to cancel each other. What I'm trying to say here, not very well, is I would increase VG1 by 10, B would go down by 10. If I decrease VG1 by 10, B would go up by 10. So the spreadsheet, ironically, this is what you learn from uh, doing these kinds of things. You learn by your failures that VG1 is proportional to the inverse value of B. Therefore, you would think that you multiply B across this proportionality, and you get VG1 times B would be equal to a constant, not 1. It wouldn't be equal to 1. It's proportional, but it's not equal to, but a constant. And it would be in volts. VG is volts per G1. This is the number of G1s. Ends up in volts. The one constant you have in the system is the battery. Battery's supposed to be constant during all this, although part of my problem with the test is the battery drifted under, especially under heavy load. Is this VB, voltage of the battery? Well, I looked into it. I'm not going to explain it. The answer is no, it's not. It's a constant, but it's apparently something else. Maybe I'll find it later. Okay. Not very good. Is this a failure? Well, it's only a failure if I let it be a failure. Let me advise you, when you do anything in life, including experiments in science, it's only a failure if you let it be a failure. If you walk away and say, okay, I'm done, close the books and quit. I used a 6.5 digit digital meter, and it was apparently not accurate enough. I could have rented a 7.5. That would rent for $300 a month, plus handling. So it would be more like $350 or something. Use a more stable power source. Better meter, more stable power source. That would cost me some more to rent. Then I got to work on those equations. If I got 7 unknowns and 7 equations, it just bugs the heck out of me. I can't solve them. Maybe they're not independent equations, and I got to look deeper. And I'll further devise a new plan, a new procedure, modify, make sure I'm doing the procedure in the good way. So it's only a failure if I let it be a failure. My name is Bobby Hilster, and I am your particle model guru. Tune in next time when I'll explain more of the universe using the particle model. Thank you for your attention.